Welcome to Antenna as a Component. Today we have a focus video about polarization, the concept of axial ratio, and we revise together about polarization efficiency. So the purpose is to discuss about antenna polarization and wave polarization. Then we will hit two explanation on a different type of polarization, including linear, circular, and elliptical, and how to distinguish between them based on the axial ratio. Finally, we will define what's called polarization loss factor, which is also named as polarization efficiency. So, what is an antenna polarization? Simply, it is the polarization of what? Of the radiated wave when the antenna is excited. Or, similarly, it is the polarization of the incident wave on this antenna received from a specific direction. And actually the antenna polarization depend on the type of the antenna. We have many type of antenna, including dipole, helix, patch, and so on. And of course, depending on the placement of this antenna in the space, the polarization direction will be defined. And there is a simple tip, or this is very detailed explanation. So simply, antenna polarization is the direction of the radiated electric field from the antenna. The second definition which we have is the wave polarization. If we have a time varying wave, so its polarization is the time varying direction of the magnitude of its electric field in the transverse plane, because as we know, the propagating wave is a TEM wave, and if we assume that it's propagating this row direction, for example, and this is its E and this is its H. So the polarization is simply the direction of the electric field, and this is just the tip here. It is again, like the antenna was the antenna polarization was the direction of electric field of the antenna, and similarly the wave polarization is simply the direction of its electric field. Now we move to the types of the polarizations, and we have three types of polarization, starting from linear polarization, which is defined as the fixed direction of electric field. So if we assume propagation is in this direction, then our field will be in the xy plane. So it can be fully in x direction or fully in y direction, or having some angle between them, and we can represent them in equation like this. So if phi is equal 0, we know that this will be a positive x-axis. If phi is 180, it will be negative x-axis. And same for y-axis, we can have also based on the angle, either it is pi over 2 or minus pi over 2, or at the end some angle between them. Now we move to the second type of polarization, which is circular polarization. And the unique thing here is that the field is actually rotating with constant magnitude, tracing some kind of circle. And it can be either right hand circularly polarized, means the field is rotating clockwise, or it can be left hand circularly polarized, means the field is rotating anti-clockwise. If we look to either of these equation, the only difference, of course, is the direction of rotation, but either we'll have here negative or positive sign. But the important thing here is the phase which we have in the equation, which force the field to rotate. To imagine this one, I brought for you this one. Assume that if we have linear polarized, you will see that only you have this kind of wave. If you have linear polarized in x-axis like this, it will be propagating like this. But because they both of them exist in the same time, and they have phase shift between them, they will be combined, and you will see this kind of propagating wave. And if you look from this direction to this propagating wave, you either will see rotating in clockwise or anti-clockwise in a circle. Now we move to the third case, which is elliptical polarization, the general case of polarization, where the electric field would trace an ellipse. And to be frank, either linear or circular polarization is just a special case of the elliptical polarization. And we can see this one from the equation defining elliptical polarization, because as we can see here, we have a phase shift term, and if actually this angle is equal to 0, what we will have, this all of this will just be equal to 1. And if this is equal to 1, we will return back to the equation of the linear polarization. And if this angle is equal to plus or minus 90 degree, this means in that case we will have here plus or minus j, mean the phase shift term, which we can see in the elliptical polarization, but we have here sine and cosine. And in the case of circular polarization, we need this cosine is equal and sine is equal to 1 over the root of 2, and this is satisfied when we have 45 degree. Finally, the general case, which is the case here, the elliptical polarization, which again we have the phase shift like the circular polarization, but the angle here, I mean the cosine term and sine term, is not exactly equal, means the angle is not 45 degrees. And here the plot of this kind of elliptical polarization, assuming propagation in the z direction. So instead of a circle, we can see an ellipse. Of course, this one is right-handed, and we can also have left-handed, like the case of circular polarization. Now we move to another definition, which is the axial ratio, which is the ratio between the major axis and minor axis of the polarization ellipse. If we brought back this ellipse shape here, and we have the major axis, so we name this one a major, and we have the perpendicular to it, we will have the minor axis, then we name it a minor, and this division will bring us the axial ratio. And in reality, we have all the antennas actually are elliptically polarized, and based on the value of this axial ratio, we approximate it to either linear, elliptical, and circular. So if it is equal 1, this is circular. If it is approaching infinity, then it is linear. And if it is something between them, we call it elliptical. Now we refresh our memory with the polarization loss factor, which we studied in different video. And polarization loss factor quantifies the reduction in the received power due to the polarization mismatch. So if the incident wave to the antenna have a polarization pi or rho I, and the antenna itself have brx, receiving antenna, then dot product of them and we take square, then we got the what's called the polarization loss factor. And why BLF is important? Because it defines the polarization efficiency, which is the fraction of the received power retained due to the polarization match. And simply, eta polarization is equal to BLF, but later we define what's called angle alpha, which is the angle between the incident wave polarization and the receiving antenna polarization, and simply it is calculated by the dot product of the two vectors and taking the magnitude, and then you get the cosine alpha. Now we are with the takeaways of this lecture. We studied together the polarization, which in case of wave of antenna it is the direction of the electric field, and we have three types: linear, circular, and elliptical. Then we understood together what's called axial ratio, which is the ratio between major and minor electric field components, and it is used to distinguish between different type of polarization. And in reality, the circular polarized will be defined as axial ratio is less than 3 dB. Finally, we revised together the polarization loss factor and its relation to efficiency, and how to calculate the polarization efficiency.